Today we are explaining the paper titled Understanding Reasoning from Pre-Training to Post-Training.
What is the central question here?
This paper asks how the quality and scale of pre-training affect later reinforcement learning, and what reinforcement learning actually changes inside the inherited policy. The authors study both questions in a controlled chess pipeline, then test the main scaling pattern again on mathematical reasoning.
Why are those questions difficult to answer with ordinary language models?
In a normal language model experiment, pre-training data is enormous and heterogeneous, so it is hard to tell whether a behavior came from the initial model or from ARL. A systematic sweep over model size, pre-training data, and ARL compute would also be prohibitively expensive, while final answer accuracy hides what happens at each reasoning step.
What does the controlled chess setup make possible?
Chess gives the study a compact action space, exact move verification, and human game data whose amounts and composition can be varied. The goal is not to build the strongest chess player, it is to make the connection between pre-training and post-training measurable.
How do the three training stages connect?
First, the models learn plausible move sequences from 50 billion tokens of human blitz on rapid games. Next, supervised fine-tuning uses synthetic reasoning traces made from sampled continuations, followed by the target solution. Finally, GARPO reinforcement learning plays verified puzzles and receives the reward only when every solve a move matches the designated solution.
Why is the reward so strict?
Each puzzle has a unique best move at each step. A wrong move ends the episode, while a correct move triggers the opponent reply and advances the state. That binary, step verifiable signal lets the researchers compare the probability of individual legal moves before and after ARL instead of looking only at a final score. Now let us see how the paper models the local return from ARL compute.
What does each part of that scaling equation represent?
R is the benchmark reward for a model with n parameters and t pre-training tokens after C, FLOPS of ARL. A ref is the fitted reward at a reference ARL budget, and B is the local gain for each tenfold increase in ARL compute. The log form is useful because the experiments cover orders of magnitude rather than evenly spaced compute values. The authors begin from a sigmoid ARL curve, but most runs are still in the unsaturated region. The local equation is its first-order approximation, so it describes the measured range. It is not a claim that reward grows without limit.
How does the initial pre-training state enter this equation?
The fitted reference reward is predicted from pre-training validation loss. Lower loss means a stronger post-ARL level at the same ARL budget. The fitted slope is predicted from pre-training tokens and model size. In short, pre-training sets both where ARL starts and how quickly it improves. The two checkpoint maps are written as follows.
Why use both the loss map and the token map?
The loss map predicts the reward level at a chosen ARL budget, while the token and size map predicts the slope of the ARL trajectory. Together with a chinchilla-style loss estimate, they turn a hypothetical recipe of model size, pre-training tokens, and ARL compute into a predicted post-ARL reward. The first scaling result compares the fixed compute frontiers.
What is the allocation pattern across those frontiers?
At low total compute, the best points use a large pre-training share and only a small ARL share. Because ARL started from a weak initial Ashanius cannot recover the loss capability. As the budget grows, pre-training has diminishing returns and the optimal ARL fraction rises. ARL consistently improves past at 1, but past at 16 is flatter for larger models, where more pre-training can be the better investment. The next result tests whether pre-training properties predict the local ARL curve.
Which relationship is the strongest evidence in this panel?
Lower pre-training loss consistently predicts higher post-ARL past at 1. And the correlation tightens from about minus 0.93 to minus 0.99 at larger reference compute. Separately, the ARL slope rises with pre-training tokens. The joint model predicts that slope better than using tokens or model size alone, although the trend is local and becomes compressed when easy benchmarks saturate. Using the fitted law, the authors search over hypothetical compute splits rather than training every recipe.
What does that extrapolated frontier tell us in practical terms?
The predicted frontier agrees closely with the measured one. Its optimal ARL share grows from roughly 20% at 50 million parameters to 28% at 680 million, while the chosen pre-training token count shows no systematic departure from chinchilla allocation. Leave one out validation gives about 0.0 to reward or MSE when the observed pre-training loss is supplied. The paper then asks what ARL changes at the level of individual moves.
How should we distinguish the three policy changes shown here?
Ground truth amplification means the correct move was already in the top 3 and becomes more likely. Tail discovery means a correct move that started below probabilities 0.05 enters the top 3. Wrong mode amplification means the correct move stays out of the top 3, while an initially preferred wrong move becomes even stronger.
Does that explain why pass at 1 improves more reliably than pass at 16?
Yes. Making one correct move more probable can raise pass at 1, even if the overall distribution loses alternative correct continuations. On hard puzzles, discovering some varied solutions helps, so ARL is not just a uniform sharpening operation. The reasoning traces provide a second mechanistic view. Because each trace is a tree of candidate move continuations, the authors can measure its width, depth, branching, and move quality during ARL.
Does ARL make the search deeper?
The traces become broader more than deeper branching and width increase, while maximum search depth stays roughly flat. Proposed moves and predicted replies improve, but continuations requiring more than 5 moves remain difficult, so better candidate generation arrives faster than long horizon search. Finally, the paper tests a predictive pattern outside chess.
What exactly was transferred to the math experiment?
The authors trained 1 billion parameter OLMO to checkpoints on a math-heavy corpus, saving checkpoints from 10 to 200 billion pre-training tokens. After supervised fine-tuning on mathematical reasoning traces and ARL on mixed math problems, longer pre-range checkpoints reached higher performance at fixed ARL compute and improved faster as ARL compute increased.
Does that make the chess numbers universal for language models?
No, it is early evidence that the qualitative relationship transfers, not a claim that the chess exponents or category proportions apply to language models. Chess has a small vocabulary, exact verification, unique solutions, and binary rewards, while language reasoning has open-ended and partial credit outcomes.
What are the main limitations to keep in mind?
The fitted law is only a local approximation over the measured ARL range, and predicting loss from model size and tokens adds error. The experiments reach at most 1 billion parameters. The hard puzzle regime is sparse, and the tree-serialized reasoning format may shape the observed search dynamics. These results are allocation guidance under the fitted assumptions, not a guarantee far beyond the training distribution.
What is the clearest conclusion after all of these analyses?
Pre-training is not merely a warm-up for ARL. Its loss predicts the level that ARL can reach, and its data scale predicts how quickly ARL improves. Starting ARL to early wastes compute on a weak initial Ashanius, but at larger total budgets say ARL deserves a growing share. The policy evidence adds the other half of the story. ARL can amplify existing correct moves, discover buried correct moves, and amplify wrong moves depending on task difficulty. That is the paper's full message. Understanding reasoning requires studying pre-training and post-training as one connected process. This wraps up our explanation.